Okay.
Hello, good afternoon, good evening, morning, good day, everyone. Welcome to the very last Geoscience and GeoWebinar, Geoscience and Geoenergy webinar of 2023. This is our 116th webinar. We started April 2020 when pandemic started. And since then, we have been hosting on a weekly basis and then lately on monthly basis the webinars. And to many of you who are going to watch this when your time zone is in more kind of civilized way to watch scientific talks. Today, Sebastian and myself are delighted and pleased to host our colleagues not from too far, from Utrecht University here in the Netherlands. Um, we are hosting Professor Alissa from the University of Utrecht, as I just said, Alissa Kotowski. Alissa is an assistant professor of structural geology and electron microscopy in the Department of Earth Sciences at Utrecht University here in the Netherlands, as I just mentioned. She's originally from Boston, MA, Massachusetts, so it's not that warmer than here. So she,
Right.
I guess, she got to a warmer place overall. I mean,
Slightly, yes.
so good move. I mean, that's fine. I mean, so and earned her bachelor's from Boston College in 2014, and then she earned her PhD from the University of Texas at Austin in 2019, where she was a National Science Foundation Graduate Research Fellow and worked on subduction zones. In fact, if you read her biography, she says about what specifically she worked on, but it was beyond my comprehension limit. So I just say she worked on subduction zones. She then moved to Montreal, Canada, where she was a postdoc, also at McGill University. She started to incorporate an experimental approach to her research, so she broadened her research expertise. And then now, as an assistant professor, she also received the very prestigious Venny Award. So she's a Venny laureate and is leading a research group that primarily focuses on the flow behavior of solid earth materials, including ice and silicate rocks, but with also emphasis on the initiation and maintenance of subduction plate boundaries, both on the modern Earth and deep in Earth history. We are very much delighted and honored to host you, Alissa, today. Thank you very much for graciously accepting our invitation. And as you can imagine, we would like to really learn about your research topic and see how is it going, what is it about. And so you need to somehow be patient enough and tolerate us and many of our colleagues who come here as curiosity to learn about what is this research topic about. So please.
Great. Yeah, of course. And I'm very excited for all of the questions of any level. So thank you so much for the invitation and thank you for the introduction. So what I'd like to do today is show you some of the work that my research group and I have been doing out of Utrecht University. And really what we've been trying to do is figure out what is the ideal formula for how to make a subduction plate boundary. And this is a very complicated and sometimes quite controversial question. But today what I'll do is try to break this down and cast it in the framework of what are the feedbacks that occur to allow a plate contact to develop. And I'll break this down into three key types of feedbacks. The first is metamorphic. So this is solid state changes in mineralogy as a function of pressure and temperature changes. Metasomatic, this is to do with the fluids in the system, how they alter the rocks that are there, and how all of these things feed into the mechanical behavior or the strength or the rheology and flow behavior of the plate boundary. And I'll highlight two different examples of these feedbacks, and I hope to convince you that these feedbacks are really important both for developing the plate boundary in the first place, but also controlling how it evolves on a much longer timescale. And I want to thank my co-authors and collaborators for all of their efforts with this research, specifically three of my master's students at Utrecht University, Tim van der Werf, Hester Smit, and Jippe van Broekhoven. They've done a lot of the work that I'm going to show you today, so now I have the pleasure of trying to synthesize all of their efforts. So if we strip this down to a really fundamental level and ask the question how to start a subduction zone, we can come back to early work from the early 2000s where Bob Stern gave us some vocabulary and conceptual frameworks to discuss how subduction zones initiate. And he broke this down into two end members. First is induced subduction initiation. This is basically where you already have a subduction zone going, but it gets plugged up. You have attempted subduction of a continental block, for example, but it's much too buoyant. It doesn't want to go down, but convergence continues. So the subduction zone has to go somewhere else. So this can occur by transference, for example, so the subduction zone jumping outboard, or polarity reversal, so just changing the direction. And in contrast to this, there's spontaneous subduction initiation. This now basically reflects spontaneous gravitational collapse of an old, dense lithosphere. This can happen theoretically at a passive margin, for example, where maybe you have old, dense lithosphere that's also weighed down by a sedimentary package, or it could happen by transform collapse, where you have a transform fault that offsets slices of oceanic lithosphere of different ages, and therefore thicknesses and buoyancies. And essentially the older, denser plate collapses beneath its own weight. And this perhaps can be facilitated if this plate boundary is lubricated already by a very weak platy mineral like serpentine. So there are plenty of modern examples of these induced and transform collapse scenarios, or at least in the modern Earth system, we see evidence for these having occurred. However, there are no Cenozoic examples of this passive margin collapse example. And in fact, this is not very surprising because mechanical estimates of the strength of these old lithospheric units actually indicates that they're too strong to just fail beneath their own weight. So this passive margin collapse example is unlikely to occur. But we're more interested in the spontaneous collapse cases in this scenario because we really want to figure out how a subduction zone starts in the first place. So rather than where a subduction zone can jump or change direction, I want to figure out how you actually get one going. Answering this question is really important because this is going to help us figure out what ignites the modern plate-like tectonic system. So more recently, we've started to move away from this conceptual framework of induced and spontaneous, and we're going towards a framework of what are the dominant forces that facilitate subduction initiation. So if we have this piece of lithosphere here, again, we have a zone of weakness. Maybe this is something like serpentine, so hydrated ultramafic material that you find in a wet mantle. And we have two end members now in terms of the dominant forcings. We can have vertically driven subduction initiation or horizontally driven. And you can also have mixtures of the two as well. In the vertically driven case, this is kind of analogous to the spontaneous collapse case, where basically you have a denser piece of ocean lithosphere collapsing beneath its own weight. Now what you can see is that there's space made in the upper plate. So you get upwelling of a stenosphere and actually the formation of a proto-4-arc spreading center. In the horizontally driven case, first you have a stage of forced convergence, and then eventually this gives way to the vertically forcing scenario where the downgoing plate, the density of the downgoing plate overcomes any resistance from the upper plate, and then it starts to collapse. Then you get this upper plate spreading and proto-4-arc center formation. The really nice thing about this is that we actually have evidence of exactly this process in the rock record. So we can now look to the rock record to figure out which of these dominant forcing modes is actually more likely or more common throughout Earth's history. So this proto-4-arc spreading center is actually exactly how you make an ophiolite. So large slab ophiolites in Oman, in Turkey, in Newfoundland, for example, are all thought to form in this supra-subduction zone, so above a subduction zone environment. And that's supported by the mineralogy, the geochemistry of the lavas in this ophiolite sequence. So the really nice thing about ophiolites is that we don't only have the upper plate here in the oceanic lithosphere, we also tend to get remnants of this downgoing plate, this young subduction zone interface. And if we can actually quantify the timing of formation of this little orange sliver compared to this green crust here, then we can figure out which dominant forcing mode is more likely. So this was actually exactly done by Carl Guillemette and others in 2018. And for the case in the very famous scenario in the Oman ophiolite, they showed from garnet lutetium hafnium ages that there's a first initial stage of horizontally driven forced convergence at about 104 million years. And this eventually gives way to the vertically driven forcing. And this is constrained by zircon uranium lead crystallization ages of plagiogranites in the ophiolite lavas. Because there's this difference now between the timing of metamorphism and the timing of upper plate spreading, we can actually quantify this time lab, subtracting the two, and show that there's an 8 million year lag between initial forced convergence and the time when the lower plate can actually overcome any resistance and create this self-sustained subduction system. One of the really remarkable things about ophiolites is that these metamorphic rocks beneath them tend to have very similar deformation metamorphic histories, no matter where we see them in the world. So this is telling us that these little slivers here, which we call metamorphic sols, are recording really fundamental processes somehow related to the formation of these subduction zones. So if we zoom in now and take a look at what these ophiolite tectonostratigraphy looks like, this green and purple here is the ophiolite sensu stricto. So this is the oceanic lithosphere. There's about 10 to 12 kilometers of crust and mantle in the Oman case, for example. And then this is in tectonic contact with this unit here, which is the metamorphic sol. So this is now the downgoing plate. And everywhere we see this intact, complete metamorphic sol, we see an upper high temperature slice and a lower low temperature slice. And these rocks record an inverted metamorphic gradient from higher temperatures at the top, so hotter metamorphic rocks, and they're underlain by these colder metamorphic rocks. If we look at a compilation of pressure temperature conditions recorded by these metamorphic sols, again, we can see that the black rocks here, the black data points, which are the high temperature sols, all enter this upper amphibolite to granulite facies conditions, and the low temperature sol rocks are much lower in the green schist facies or so. And again, this is consistent no matter where we're looking at metamorphic sols all over the world. So now we can couple these petrologic observations, which help us constrain the pressure temperature conditions of the high temperature and low temperature units. And now we can put even more information on their formation histories using geochronology. So we can actually constrain the timing of metamorphism in the high temperature and low temperature units. And if we do that, we see that the high temperature unit actually sustains these very hot conditions for upwards of 10 million years during the first stages of convergence. But then these low temperature rocks, which actually probably have slightly higher pressures than these white circles here, these rocks actually form later at about, for the Oman case, at about 91 million years. And they record very rapid transitions to these colder conditions. So now we not only have pressure temperature conditions of the formation of these units, but we're also getting a sense of time. So these rocks are hotter and they form first. These rocks are colder and they form later. And this becomes very important because if we have constraints on temperatures and time, then we can infer cooling rates of the plate interface. We know from these rocks that during subduction initiation, the plate interface starts very, very hot. So if you know about modern subduction systems, you know that granulites don't belong there. We typically want blue schists and eclogites along this trajectory. So we start hot and the interface has to cool down to make those hallmark blue schist and eclogite material. So what this means is the first stage of underthrusting is hot, entering this granulite facies, lasting for about 10 million years. But at some point, this gives way to this colder trajectory along this red arrow, and this will continue to cool down according to the rate of plate convergence and the age of the incoming plate, eventually maybe creating these blue schist and eclogites, high pressure, low temperature metamorphic assemblage. And so the relationship between the timing and the temperature allows us to make the inference then that we actually have multiple stages of the subduction initiation history recorded in this metamorphic soul. The slow cooling that we see, or the protracted record of high temperature conditions in the high temperature soul, probably means that the initial underthrusting was extremely slow. This then gives way to much faster cooling, which reflects much faster plate speeds. And this led myself and a few other people to make the interpretation that these high temperature and low temperature soul slices actually record this fundamental transition in forcing, this forced or horizontally forced subduction initiation to this self-sustained or vertically forced subduction initiation. So really the takeaway, I think, is that this transition from high temperature to low temperature soul reflects that onset of when the subduction zone unzips and really turns on. So if we want to understand why this is the case, why we actually get this transition from slow plate convergence to fast plate convergence, slow cooling to fast cooling, then we need to look at the metamorphic soul in more detail to figure out the reason why. One of the things we can do is look at interface rheology, because this dominantly controls large-scale plate dynamics. Here are some really nice models from Whitney Bear and others from 2022, and they show that the actual interface viscosity, so the really thin layer that accommodates strain along this plate interface, the viscosity and the rheology of that thin layer has a huge implication for large-scale plate speeds. So, for example, if you reduce the interface viscosity by several orders of magnitude, you can actually get increases in plate velocity. And this is going to have fundamental implications for things like cooling rates, what metamorphic mineralogy is stable, and all of these things feed into one another to generate this highly localized, fast subducting plate system. Another important thing to think about is, how does serpentine actually play a role? Because a lot of people think that serpentine is necessary and actually to create a plate boundary. This is because it's an extremely weak and low viscous material, low viscosity material. So maybe if we're cooling things down and we actually get serpentine to stabilize, maybe this isn't a reason why we have increases in plate velocities and cooling, etc. So we need to keep in mind how serpentine is actually playing a role in this system. So there's this nice call to action from Bob Stern from 2012, where he said, in order to understand subduction initiation, study 4-hour crust. And in order to study 4-hour crust, study ophiolites. And so for today, what I suggest to do is to study subduction initiation. We really need to figure out the rheology and viscosity of the rocks on the interface as recorded by metamorphic souls. And we will still do this, again, by going to these ophiolite complexes. And what I want to do is start to bridge the gap between this point A and point B, where we have far field plate reorganization, broadly speaking, some series of processes that occur leading to subduction initiation successfully. But we know that in this black box, we need to have these metamorphic, metasomatic, and mechanical feedbacks, and they need to be facilitating this plate boundary formation. And what I want to do today is frame this from the avenue of temperature. So we know that the temperature is changing. We know that rocks start hot and they cool down. So how does temperature actually trigger these metamorphic, metasomatic, and mechanical feedbacks? And we end up seeing these really interesting connections between the influence of temperature on metamorphic mineralogy, the stability of fluids, and rock strength. And ultimately, by looking at these things, we're going to figure out what the materials and conditions are on the plate interface, how this alteration in metasomatism is occurring, and how this all feeds into rock rheology. All of this needs to lead to the implication that the rocks are weak enough to actually localize strain, facilitate fast plate speeds, and keep rocks weak over geologic time. So we're going to go through a few examples of these feedback loops here. And by the end, I'm going to be able to answer both of these questions. The first is, why does subduction zone initiation have this sluggish start? Why do we have this slow forced convergence first happening? And what controls that time span? And why does that then give way to the vertical forcing to actually get fast subduction plate speeds? And the second question is, what role does serpentine play? A lot of people say that it's necessary for subduction initiation. Can we find evidence in the rock record that it is playing a crucial role to allow strain to localize? So to answer these questions and to go through these feedbacks, I'm going to take you on a bit of an excursion across this newly forming plate boundary at the boundary between the downgoing plate and the upper plate. So this metamorphic soil ophiolite contact using rocks from Mont Albert in Canada. So a little bit more context. So Mont Albert is an incomplete Ordovician ophiolite. It's related to a series of Quebec ophiolites that includes the most famous example of the Bay of Islands complex in Newfoundland. The rocks here are part of the dunnage zone. What this means is that they're part of an Ordovician ocean basin. This is related to the Iapetus Ocean. It was situated outboard of the Humber zone, and this comprises the passive continental Laurentian margin. This is what the ophiolite complex was emplaced onto during the tectonic orogeny about 450 million years ago. If we zoom into a geologic map of Mont Albert, you can see the nice colors on the right here pointing to the different lithologies. So this orange unit is a large tract of tectonized peridotite, and it occurs in thrust contact along this red line with this purple unit, the metamorphic soil. At the topmost part of the metamorphic soil, we have garnet-bearing amphibolites. These are really beautiful rocks, very high temperature rocks at the border between amphibolite and granulite facies conditions. And also at this contact where this red thrust is, we see quite a lot of serpentinization of the mantle. So a lot of fluid ingress into the mantle, which hydrates the mantle and creates this serpentine, which is extremely weak and a platy mineral. We also have this orange unit over here, this Mont Olivine, and this is where you see the freshest unserpentinized peridotites in the unit. So I'm going to show you a few samples from this mantle wall sequence up here, but I'll also contrast what we see on mantle wall with one sample from Mont Olivine, so you can see what the beautiful, fresh, unaltered mantle looks like as well. And as a reminder, this is where we are tectonically speaking. So when we go to mantle wall, we have this contact between the downgoing plate. Now this subduction zone interface is in this blue-purple color. And we're right at the margin between that and the immediate upper plate. So this developing four-arc mantle wedge. This is a photo of mantle wall, and it's a really spectacular, intact, fossilized paleoplate boundary. So these orange-brown rocks here are the mantle, and you can see this really beautiful layering here. This is a deformation-related foliation in the mantle, and there's also quite a lot of compositional layering here as well. Then you can see there's a little saddle up here and a slide. And this basically marks the transition between the lowermost part of the mantle and the underthrust metamorphic soil. There are some grubby exposures of the soil in the trees over here, but basically as soon as you start where the trees are, that's where the metamorphic soil is. Nothing really likes to grow on the peridotites, but things like to grow on the metamorphic rocks. We see really spectacular similarities here in terms of the structure and the lithostratigraphy, as is seen in Oman. So from top to bottom here, we have this upper plate, the bottom part of the upper plate, this is the mantle wedge, and then this is in thrust contact with this underlying metamorphic sole. Previous work by Philippe Bigard and others have distinguished different parts of the metamorphic sole into this high temperature A and B and low temperature units. So what I'm going to do is show you 4 samples that correspond to dry unserpentinized mantle, serpentinized mantle, high temperature rocks, and low temperature metamorphic rocks. The point now is to compare and contrast mineralogy, evidence for deformation features, evidence for deformation mechanisms and rheology, and try to pinpoint where fluids become important in the development of this plate boundary. So here's a really beautiful example of what the fresh, dry peridotites look like. This is a sample from Mont Albert where there's no serpentinization at all. These are very fine-grained spinel peridotites. The fact that they're spinel-bearing, this is the aluminum-rich phase, this is telling us that we have pressure somewhere between 5 and 20 kilobars. And the fact that they're so fine-grained and unserpentinized indicates that they're deforming somewhere above 600 degrees. Serpentine becomes stable at about 500 degrees, so we have to at least be above that. But the fact that they're so fine-grained probably indicates that these rocks are deforming under relatively cold conditions, at least as far as peridotites go. So when we're in the 700, 800 degree range for peridotites, that's actually quite cold for mantle deformation. If we look at some microstructures of these rocks, we can see really beautiful distributions of different grain size. There are coarse-grained layers here and really fine layers here, which are pointing to evidence of ultramyelinization of this dry, fresh, unserpentinized mantle. And in cross-polarized light, we can start to see more evidence for this dynamic recrystallization. We can zoom in and see this undulose extinction in these olivine porphyroclasts. You can see this change in birefringence color from green to black to blue, etc. This undulose extinction is telling you that there's intracrystalline plastic strain inside of these clasts. The coarse-grained portions are mostly exhibiting this. And if we compare the compositions of orthopyroxene and clinopyroxene that are forming in these fabrics, we can actually calculate equilibrium temperatures of deformation related to this event. And based on the major element exchange of things like calcium, magnesium, and iron, we can calculate that these pyroxenes, these 2 pyroxene thermometers, are indicative of temperatures of 750 to 850 degrees Celsius. And these are very similar temperatures for similar textured peridotites as seen by Agard and others in Oman. So the inferred deformation mechanism for these rocks is dislocation creep, and that's supported by the evidence of this abundant undulose extinction, these porphyroclast and mantle structures, lots of evidence for small equant recrystallized grains. And this is reflecting the movement of dislocation, so line defects, through the crystal lattice in response to applied shear stress. And in doing so, in actually moving these dislocations through the grains, you accommodate shape change, you make deformation happen, and that is what produces things like undulose extinction and eventually recrystallization. Because these are deforming by dislocation creep, we can measure the recrystallized grain size, and there are empirically derived relationships between recrystallized grain size and flow stress. So now we can get a sense of how strong this rock actually was. And if we do that, we estimate stresses on the order of 100 to 150 megapascals. These are moderately high stresses, but consistent with the fact that these rocks are deforming under relatively low temperatures. Now, if we go back to mantle wall, we can start to think of the importance of serpentinization. We've done a lot of work to characterize differences up and down mantle wall. And basically what we see are different units reflecting different amounts of serpentinization. You get more serpentinization coming in the closer you get to the plate boundary. This reflects the more abundance of fluids coming from the plate boundary. If we go in this trend of decreasing serpentinization from the contact upwards, we can look at differences in what the rocks look like. At the contact, where we see a lot of serpentinization, there are these really beautiful banded red, orange, white serpentine mylanites. Going up the wall, we transition into these gray-white mylanites with locally very strong thrust sense of shear, indicating a top to the north thrust sense. And then going up further, we have these orange-brown porphyroclastic peridotite mylanites with less serpentinization. If we look at these serpentine mylanites with the most serpentinization in microstructure, they're also extremely beautiful, and these textures are really, really incredible. So what we can see here also are these compositional layers here. We see these wispy orange, red, black layers here. These are actually hematite layers. They locally form these little boudins here with this white material. And in cross-polarized light, you can see this compositional banding even better. Now, these yellow-orange, this is actually where we see quite a lot of relict olivine. So even though these rocks are heavily altered and heavily hydrated to make serpentine, there's still a lot of leftover olivine. So that means that the serpentinization process has not gone to completion. If we zoom in, you can see that relict olivine here in these cores surrounded by these serpentine layers. And Raman spectroscopy confirms that these serpentine minerals are actually lizardite. And again, as I said, these red layers here are hematite. The fact that this is lizardite is really important because the polymorph of serpentine that's stable depends on temperatures and kinetics of serpentinization. Lizardite only forms at a maximum of 300 degrees Celsius. So this tells us that these rocks are serpentinizing under extremely cold conditions. Remember that the peridotite mylanites formed at about 800 degrees. So this is much, much, much later after the plate boundary has cooled down substantially. Now let's take a look at the metamorphic soul. So now we're underneath the plate boundary at the uppermost part of the metamorphic soul, the high temperature unit. We see strongly foliated rocks making these nice ledges here. And zooming in, we can see interesting relationships with quartz veins. We do know quite a lot about the rheology of quartz. So by looking at quartz veins, we can make inferences about the relative strength of these amphibolites for which we don't have as good rheological constraints. But sometimes we see that the quartz veins are basically isoviscous, so similar viscosity, deforming in very similar ways to the surrounding amphibolites. But in other cases, they make nice little boudins, indicating that the quartz is maybe slightly stronger. We also see these nice rootless isoclinal folds in quartz veins, telling us that these rocks are deformed to relatively high strain, even though it's quite difficult to see. Locally, we have these really gorgeous garnet amphibolite mylanites, and you can start to see these garnets that are being deformed and making these nice little recrystallized tails. If we look at the mineralogy in these rocks, we can use major element exchange between stable minerals, garnet and pyroxene, to also calculate equilibrium temperatures. Again, these are consistent with 700 to 800 degrees Celsius. So similar in nature to the temperatures of peridotite myelinization. In thin section, the high temperature soul rocks closest to the contact exhibit a ton of dynamic recrystallization in the quartz layers. And you can see this in cross-polarized light again, where we're seeing undulose extinction, subgrain formation, and grain boundary migration. In a sort of textbook sense now, we're in this recrystallization regime and this one where we see these small equant grains forming at the expense of large grains and these amoeboid sutured grain boundaries. So these different textures are pointing to different mechanisms of recrystallization in the quartz, which we can use to infer something about the conditions of deformation. But we can also use quantitative techniques like electron backscatter diffraction or EBSD to really dig into what the record of deformation mechanism is in these quartz layers. So EBSD is an electron microscopic technique. What you do is basically raster an electron beam over a prescribed area of your thin section. And what you do is collect what we call these Kikuchi bands, which you can see in this little GIF on the left. And these are indicative of crystal lattice structure and orientation. So if we do this over a large thin section area, you can see what minerals are there and what their orientations are. So we can plot this data just by what minerals are there, which I'm showing you here with this phase map. We can also color code these by grain orientation and look at things like intracrystalline plasticity and undulose extinction as well. We can also plot the data according to grain orientation in pole figures. Basically, this is just showing you the orientation of grains in some reference frame. So now we have all of our grains showing these clusters of orientations for quartz only, showing that there's a 001, so C-axis lineation defining pole figure here. All you need to know about this is that this means that this texture forms under high temperature conditions. This is consistent with what we know from the petrology. This makes perfect sense. The dynamic recrystallized mechanism that we see here is also indicative of low stress. And if we use the quartz piezometric relationship between grain size and stress, we get much lower stresses here on the order of 5 to 30 megapascals. This is consistent with this type of slip system, making this pole figure, the inference that we're deforming under high temperatures, etc. So much lower stresses than we saw in the mantle. Now, the last rock I'll show you is this low temperature sol. And I hope you can see that there's a lot of difference here compared to the high temperature rock. We can see polyphase deformation much more clearly in the low temperature sol. This produces strong cleavages. There's a foliation that's refolded here. And this cleavage tends to form by the alignment and recrystallization of platy and sheet-like minerals. So there's more micas in here, for example. In thin section, you can see that in general, the grain size is much, much smaller compared to the high temperature rock, and the foliation is extremely strong, and there's a lot more heterogeneity here. There's a lot more different types of minerals. We can see amphiboles, there's epidotes, there's plagioclase as well. And if we compare these sorts of textures to other work that we've done on similar types of rocks from Oman, we can see that the dominant deformation mechanism here is more dominated by dissolution of material and reprecipitation. So you're actually dissolving material and moving it along, and you can grow minerals like amphibole, for example, by this solution creep process. And you can actually see really nice evidence for this in zoning of minerals, for example, cores and rims going from actinolite to edenite. And if you speak amphibole, what this means is that you go up temperature and pressure as you make this foliation. So we can actually see evidence for this solution creep process as these rocks are transecting pressure temperature space. And in this case, the amphibole plagioclase thermobarometry is the tool that we use to quantify pressures and temperatures. And this is consistent, again, with lower temperatures of metamorphism. So we have lower temperatures in the low temperature sol, and we see corresponding differences in the microstructures and mineralogy, where we see more mixing of minerals, finer grained material, and importantly, a different deformation mechanism. We see a switch from dislocation creep in the quartz-rich rocks, the quartz layers that were preserved in the high-temperature garnet amphibolites. Now we're deforming by a dissolution precipitation creep process. So distinctions in rheology between the high-temperature and low-temperature sols. Okay, so now I just want to spend a few slides going through what all of this means. So the first thing that I'll come back to is the significance of serpentine. We saw evidence that the peridotite myelinites form before fluid ingress and serpentinization. And based on the temperatures of deformation, we can infer that they form a lot before the ingress of fluids. However, they managed to localize strain anyway. We saw those beautiful shear bands in the dry ultramyelinitic Mont Albert rocks, and the incredible grain size reduction by dynamic recrystallization clearly has an important role to play. Based on the mineralogy that we see and inferred PT conditions during subduction infancy, we know that we're well outside of the stability field of serpentine. The serpentine that we see forming in those nice lizardite myelinites from mantle wall can only form at maximum 300 degrees. This means that this fluid ingress must happen way after the formation of the plate boundary. But we do see quite a lot of thrust-sensitive shear in those lizardite myelinites. So maybe this lizardite serpentinization is important for lubricating the plate interface during the abduction process. And the last thing that I want to talk about is the significance of the inferred rheology from the metamorphic soul. So we can start to put quantitative constraints on rock strength and viscosity by using published empirically derived constitutive equations describing flow behavior or flow laws. These are laws that are quantified in the laboratory by squishing rocks, and we can actually use these laws to make estimates about rock strength. So we can estimate appropriate strain rates for early stages of deformation based on the observed thickness of the shear zone and the inferred very slow convergence rates. So with the convergence rates and shear zone thickness, we can put an estimate of strain rate of about 10 to the minus 13 per second. If we do that and we plot olivine flow laws for the conditions that we know these rocks are deforming at Mont Albert, for example, then we actually get stresses that are quite consistent with our piezometric estimates. So this is very nice. If we play the same game for the metamorphic soul rocks, we get much lower stresses, but still in the ballpark of what we estimated from piezometry. Now, the important thing is that we can use these stress estimates now with the calculated strain rates to estimate viscosity. We can do that based on this simple relationship. And the important takeaway now is that even though the stresses are pretty low for the crust and maybe even moderately low for the mantle, the viscosities that those stresses yield are relatively high. And that's because the strain rate is very low. The important thing now is that as you start to refrigerate the interface, as you start to cool it down by advecting cold lithosphere, the viscosity is going to increase a bit. It's not going to increase very much for the crustal rocks, but it's going to increase a lot for the mantle, to the point where it's going to be basically prohibitive to localize any more strain there. But you can continue to localize strain in the high temperature rocks until this garnet amphibolite is no longer metamorphically stable. At that point, what's going to happen is the low temperature soul is going to form. These epidote amphibolites start to be created along the interface, and they have a very different rheology, a very different viscosity. What that actually shows is that through time, as we cool the interface down, by changing the metamorphic rock type and the deformation mechanism, this leads to an actual plummet in the viscosity of the interface. This purely reflects cooling of the plate boundary, changes in stable metamorphic rock types, which feed into changes in deformation mechanism and microstructure. All of this leads to this plummeting of the viscosity of the interface. Why is this important? This is important because we've already shown that the interface viscosity is fundamental in controlling plate speeds. So if we now have an example where we know that the interface viscosity decreases as a function of time, which reflects temperature, then we can actually have a mechanical explanation for changes in plate rates. For example, from this 10 to the 20 down to 10 to the 18, we can actually get changes in plate rates or acceleration in plate rates from 5 centimeters per year to upwards of 15 centimeters per year. This could potentially explain that transition from stagnation, from sluggish start during subduction initiation, and this transition to this unzipping, this rapid self-sustaining subduction, where we have rapid plate speeds. This feeds into faster cooling rates. This feeds into different metamorphic rock types, which feeds into different deformation mechanisms, etc. So this cooling, this temperature reduction is the only factor that needs to change to trigger all of these really fundamental changes that can lead to viscosity reduction and plate boundary formation. And with that, I will leave this conclusion slide up here. And I thank you for your attention, and I'm happy to take some questions.
Well, thank you very much for this fascinating lecture. We were exposed to a stream of new knowledge, at least from my side. So it was really informative, and thanks a lot for this very comprehensive and very illustrative lecture. So we have a number of questions posted, and we are short in time. So I hand over to Sebastian to highlight them for you and ask your comments about them.
Great.
Yes, thank you very much also from me, Alissa, for a really nice talk that brings me back to some of my undergraduate days when we looked at metamorphic rocks in the Alps a lot, but in much less detail and much less insights than you present here. Without further ado, to some of the questions that broadly fall into sort of imaging and modeling aspects. So Menji Zhao asks, thank you for the great talk. How can these rocks, these situations be imaged in real life? And can we do some geophysical monitoring, or is it mainly based on field studies and geological measurements?
Yes, that's an excellent question. Thank you for the question. So we do have some ability to image a bit of what's down there using things basically like seismic tomography. We can also use things like shear wave splitting studies to get in the sense of what the sorts of deformation or anisotropy is down there. But unfortunately, we cannot directly measure exactly what is down there. And even worse, we really don't have any good ways to measure the rheology of the rocks down there. So what that means is that it's really necessary to do these field-based studies, but to couple them with what we know about the plate interface from these geophysical surveys and what we know about rock rheology from experimental studies to try to understand what the rocks actually mean. So one of the big sort of pushes now is to really try to quantify what the rheology of these important minerals are, things like amphiboles, things like epidotes. There's a lot of groups working on that. And so hopefully that will allow us to make even stronger connections between what we see in the rocks and what it means quantitatively in terms of rock strength or viscosity. So basically we're kind of working with sort of a double-edged sword by trying to look at the rocks and infer what they mean, but we're struggling a bit now because we don't yet have all of the tools that we need to actually interpret them quantitatively. So that's why we look at things like quartz as opposed to amphibole and all of that. But that's a great question.
You mentioned quite casually, it cooled down from 800 to 300 degrees, which is in our world just really, really, really hot.
Yeah.
I think every lab technician faints a little bit if you
I know.
want to do experiments with this. Which brings me to to question from Arthur Castiel. Says, sorry, that's the wrong one. He says, thank you very much for the comprehensive talk. Even though I'm not in this field, please allow me to ask, can these be modeled in the lab? Is there anything you can do in terms of laboratory-based research?
I guess that's a difficult question to answer. I guess what type of laboratory research is the question, but I think one way to answer that is there's always things to do in the lab that is relevant for these sorts of problems and just shear zone problems in general, not necessarily just subduction initiation. But so things to do in the lab could definitely be more deformation experiments, so more and better trying to understand the rheology of the minerals that really, really matter. So amphibole being a really important one. There's also things to do in sort of an analog sense. So playing with, similar to those numerical experiments from Whitney Bear and others, playing with the effect of viscosity or degrees of coupling and seeing how that affects things like dynamic topography in the upper plate or stress and coupling across the plate interface. Those are definitely things that more work should be done because I think we see a lot of evidence, and no structural geologist would argue with this. We see a lot of heterogeneity in these shear zones, and we see a lot of change in mineralogy and rheology through time and through conditions. And quantifying that and figuring out the implications of that, I think is a very exciting place that this sort of research is going. And there's a lot of room, broadly speaking, in a laboratory sense to study that.
Thank you. And in passing, you answered another question from Menji Zhao, asked how heterogeneous these rocks are. You said they are indeed very heterogeneous.
Yes.
You talked about modeling of subduction zones. There are quite a few questions that relate to this, and trying to summarize them here, which are essentially around the questions are: what are the constitutive laws that you need for numerically modeling these systems? And do you need, what was the second question? Are we studying the mechanical properties of these rocks, or do we need elastic plastic properties? What kind of rheological behavior do we need to know to get really good insights into the numerical simulation? So essentially, what do we need to know to get some really good numerical simulations going?
Yeah, absolutely. So what we really need are more flow laws that are appropriate for things like garnet amphibolites. So luckily, this brand new flow law from Wang and others from 2023, this yellow curve that I'm plotting here, this was just published a few months ago. And so this is actually well, it's not the first, but it's the most recent and one of the strongest, I would say, as evidence that these rocks can deform by dislocation creep, which is very exciting because there's a lot of debate right now about whether the stresses required to get something like dislocation creep in a garnet amphibolite would just be prohibitively high. So I think this flow law suggests that actually that may not be the case, that we actually can see that sort of deformation mechanism in these rocks. But so basically what we need is more constraints on the relative importance of Newtonian and non-Newtonian rheologies of rocks that occupy the interface, and how those change through pressure and temperature space and as an effect of grain size and phase mixing and fluid content and all those things. And of course, each of those things is PhD worthy, I would say. So there's still a lot of work to do. But I would say in the meantime, as we're kind of working on those things, the sort of study that I'm doing here in terms of looking at the rocks, trying to make inferences about what flow laws are appropriate and what that means in terms of stresses and viscosities, we can use flow laws that already exist as sort of analogies or to be analogous to the materials that we know are there, as long as we can justify that the rheology is similar. So I think if we start to incorporate these rheologies and these appropriate flow laws, which we can justify based on observations from the rock record and from microstructures, if we start feeding these into numerical models and seeing the effects like Whitney Bear and others have shown, the effects of viscosity on things like plate speeds and upper plate dynamics, then we can really start to push forward, even while we're waiting for more flow laws from the lab.
Thank you. Then we have, again, so two questions somewhat related, and they come from Artur and Herminio. And Artur wonders, just get the right question up. What happens when these rocks go cooling? They experience thermal stress, and could they actually crack as well?
Yes, excellent question. So we do see actually quite a lot of evidence of brittle deformation in some of these rocks as well. There are some suggestions by Matthew Surrey and others that even amphiboles will start to break brittly under these high pressure conditions. And so that's absolutely possible as an option on the list of deformation mechanisms. I think in general, the confining pressures are still relatively high and strain rates low enough that brittle deformation is not as common. So I haven't seen too much evidence in my amphibolites for that, although it's very dependent on the mineral, of course. So the garnets and the squished garnets in one of the rocks that I've shown you, those actually have really beautiful fractures running through them as well. And those are probably forming under high pressure conditions. So I think at some point, brittle deformation does, of course, occur when you start to really bring these rocks to very lower pressures and cooler temperatures. Then, of course, you get the transition to more brittle. But I think for the most part, what we're seeing in these high temperature and low temperature soil rocks is distributed ductile deformation with minimal evidence of brittle deformation, basically with the exception being if you have a high pore fluid pressure, then you can get some basically like fracking and veining and that sort of thing. And that tends to be where the quartz veins come from, actually.
So that, thank you, Yusuf. Probably in passing answered most of the next question. Are these plates porous? Do they contain, or these rocks porous? Do they contain any water?
There's absolutely water there, and it's basically going to be at grain boundaries in this case. So, of course, there's going to be things like nanoporosity, and if you have metamorphic phase changes going on, you can get really small scale, nanoscale changes in porosity. But in general, I don't think of these rocks as porous in that sense. Basically, there is a fluid there. It's absolutely important. It's driving metamorphic phase changes. It can contribute to elevated pore fluid pressures, and therefore maybe sort of pseudo-cyclical brittle deformation because of those transient elevations in pore fluid pressure. But in general, any porosity or anything like that is long gone by the time you get to things like amphibolite to granulite facies conditions, based on metamorphic grain growth and things like that.
But isn't there some form of, and maybe mixing things up, but isn't there some form of water above the volatiles, dewatering going up above the subduction zone that then, drives formation of magma chambers and volcanism?
Yes,
So
absolutely.
that's all
So,
when at lower temperature, what you would classify at lower temperatures and lower pressures.
yes. Right. And that's one of the really, really interesting sort of upper plate features of the evolution of a subduction zone. So this first stage of volcanic event that you see is this proto-forearc spreading. And that's essentially a spreading ridge right above the plate. And that happens at this first stage of, spontaneous collapse of the plate interface. But then much later, actually, you'll get development of a mature volcanic arc. And that also reflects sort of depression of the slab top geotherms, and then sort of an equilibration of where the water that is then channeled into the subduction zone will then be metamorphically dehydrated and released into the upper plate. And so in this case, because these rocks are so hot, they seem to either hold on to whatever water they can or dehydrate at relatively shallow conditions. And there is some evidence that dehydration or even melting of the metamorphic soil imparts chemical signatures to the ophiolite lavas above them. So there's definitely some sort of geochemical connection between dehydration of the metamorphic soil or melting because it's so hot and what's happening in the ophiolite lavas above. But all of that is happening well before establishment of a mature, in a sense, volcanic arc, which would be later.
Well, thank you much again, Alissa, for a really interesting talk. I think we all learned something very new today. And with that, and thank you to the audience for some great questions. And with that, Hardy, back to you.
Yeah, thanks very much, both of you, and also the audience for these great questions. And you made us quite proud to stand quite strong in front of external researchers to the community. So they tried their best.
Those were excellent questions. Thank you so much.
Of course. Thanks a lot for this to the audience, especially those who are watching this also later in the day. This is the end of 2023 webinar series, and then we are thinking about the future with Sebastian deeply about the future of this channel, and we will keep you posted. So until next time, stay happy, healthy, and well, I used to say tuned in, but we don't know when the next one will be. So please stay happy and healthy for the time being. All the best, and thanks a lot again once more, Alissa.
Great. Thank you so much for the invite. This was a lot of fun. Thank you.
Bye-bye.
Bye-bye.